Hi everybody, today we're going to talk about quantum mechanics again. We're going to do something very interesting. We're going to move from the early 19th century right through the development of quantum mechanics and end in the present day with the possible interpretation of quantum mechanics as infinite branches of a multiverse. In other words, we're going to go from what is very commonsensical and observable to the crazy inverted reality of quantum mechanics and how it tears apart all of our assumptions and common sense about the world in which we live. But first we have to start with a classical experiment called the Young double-slit experiment. Bear with me while I explain this because it's absolutely crucial foundation to quantum mechanics. This one experiment can explain all of quantum mechanics. Well, it's actually very straightforward. If you shine a light at two slits, which I'll draw here, we have a light source here, say, and we shine it on two slits. What doesn't happen, you don't just get two kind of bright spots here and here. What actually happens is what we call an interference pattern. Essentially, the light waves come in from here, and you can imagine that the waves are actually as if these are two new transmitters. And what happens is that light waves, the peaks reinforce, the troughs do as well, some of them cancel out, and what you get is what's known as an interference pattern. Bear with me because I'm not very good at drawing these, frankly. You get something like this, and then kind of peaks or troughs within this. That's a very poor drawing, so I'll put an actual experimental version on the screen now. But effectively, you get alternating patterns of bright and dark, an interference pattern. If you chuck two pebbles into a lake, you will see that they create ripples, and as those ripples hit each other, parts of them reinforce, peaks hit peaks and become even bigger peaks, then sometimes troughs hit peaks and cancel each other out. That's what's called an interference pattern to two waves. And it was this Young slit experiment shining that light at those two slits that, in those days, proved that light was a wave, because only waves can produce such an interference pattern. Then Maxwell came along with his equations of electromagnetism, and you had the mathematical basis for light as a wave, and everybody was happy. But there was a problem. There was one experiment that just didn't go with the script, and that's called the photoelectric effect. This is where you shine light of sufficiently high frequency of metal, and the metal will emit electrons. Why did this not accord with classical understanding of light as a wave? Well, first, it didn't depend on the intensity of light, only on its frequency. You could shine light of incredible brightness, but if it wasn't a high enough frequency, no electrons were emitted. Below a certain frequency threshold, no electrons at all. In a classical theory, you would have expected the kinetic energy, the energy of the electrons emitted, to depend on the intensity of the light. The more intense the light, the more energy being delivered per second. But this wasn't the case, they were dependent on frequency. And furthermore, if the light intensity was low, you would still expect in the classical theory the emission of electrons, which would just absorb light over time. Maybe they'd take longer to be emitted, but they would be emitted. None of this was observed, and it was an immense puzzle and was not reconcilable with classical understanding of light as a wave. This is where Einstein comes in. Many of you obviously know Einstein for his theory of relativity and his work on cosmology, but his Nobel Prize was actually not for these things, it was for his explanation of the photoelectric effects, the experiment I just described. And what did he say? He said, no, light is not a wave. To explain this phenomenon, light is a particle that delivers energy to the metal in proportion to its frequency. The energy is proportional to the frequency. That means that only light of a sufficient frequency would deliver enough energy to dislodge an electron. And so light has suddenly become a particle. So on the one hand, we have the Young double-slit experiment, light is definitely a wave, and we have Einstein's explanation of the photoelectric effect. Light is a particle. And so where are we at this point? Well, we've got light as a wave, light as a particle. And the same thing is true of electrons and all other subatomic particles. Some things can be explained by it being a wave, and some things can be explained by it being a particle. And the most striking demonstration of this was returning to this double-slit experiment. Instead of a light source with single electrons, you can fire single electrons at this double slit. And what do you find? You actually find that they build up an interference pattern. As each electron hits the screen, you'll find that most electrons hit here, very few here, very few here, and electron by electron, you build up an interference pattern. In other words, we are firing individual particles at a double slit, but producing a wave-like pattern of interference. This is known as wave-particle duality. It means that particles have the property of waves, waves have the properties of particles. An electron is not just a solid object, it's a wave as well. And that is the fundamental of quantum mechanics. And how do you explain this philosophically? In quantum mechanics, electrons are not particles, they are probability waves. What does that mean? It means that they have a probability of being any point in space, and that's called the wave function of quantum mechanics. The probability of finding an electron in a location is called the wave function. Just like a light wave interfered, what's happening in this experiment is that the electron has a wave function. A probability wave goes through the double slits and interferes like this. The probability wave interferes with itself, and so the probability of finding an electron on the screen is this double slit interference pattern. That's the explanation mathematically, and it works. But we have completely upended reality with that. Physics is no longer deterministic. We have to speak in terms of particle waves of probability. And until we observe that particle, we cannot tell you where it is. It's everywhere and nowhere. So we have a bit of a problem here, because we're not used to talking about things in terms of probability waves. How do we interpret this? Well, the most common interpretation of quantum physics is called the Copenhagen interpretation, which states that an electron or any other subatomic particle occupies every single possible state at once until it's observed. That's what I mean by the electron's everywhere but nowhere. And when you observe it, it is known as collapsing the wave function, and it goes from being a probability wave to being a discrete particle at a point in space and time. This runs into lots of problems that we'll discuss in a subsequent video, but namely, what's an observer? You and me, a bird, an insect, an inanimate object, all kinds of philosophical problems with that, but that's the one that's most accepted by physicists. There are other interpretations, and one of the most kind of talked about ones recently is called the many worlds hypothesis. The many worlds hypothesis states that there isn't really a probability. What happens is that every time you make an observation, every time you perform a quantum experiment, there is a branch in reality. So all possible results of an experiment exist in simultaneous strands of reality. And when we make the observation, we, the humans, or our present form, our reality, continues along one line. We only know this one line, one trajectory of reality, always branching for every quantum possibility. But there are infinitely many other worlds where the other quantum probabilities have been realized, and we have an entirely different universe. So, which one of those is correct? Well, that's a subject for our next video, when I'll be discussing in more detail the Copenhagen and many worlds interpretation of quantum physics and the problem of Schrödinger's cat, and answering the question, if we don't know anything, if everything is a probability, well, then what actually is reality? What reality are we living in now? Are there infinite versions of ourselves existing in parallel worlds and parallel quantum realities? For that, I'll see you next week.